Let's keep going with part 2 of the solo answers. Which portion of the electromagnetic spectrum requires the least amount of energy to communicate through space? Here's our electromagnetic spectrum. We know it high frequencies have short wavelengths. They also require high energy. If we want low energy, we need a low frequency, large wavelength. That's why we use radio waves. A message from Earth travels 5.46 times 10 to the 10th meters at 3 times 10 to the 8 meters per second. That's the speed of light. How long does it take to receive the message? Here we're dealing with time. We're looking for time. We know a distance and we know a velocity. There's our formula. Velocity equals distance over time. One of the first formulas we learned all year long. We plug in our velocity of 3 times 10 to the 8th. We put in our distance of 5.46 times 10 to the 10th. To solve, we switch out the t and our velocity. If our variable's down below, we can switch it out for the variable or value that's out by itself, and then we just divide. To plug this into your calculator, it would be 5.46 E10 divided by 3 E8. The E represents times 10 to the power of. Should get 182 seconds. And this is because even though light travels really fast, literally the fastest thing we've ever observed, it has to travel a great distance, so it still takes time. Communication is not instant on Mars. As the message travels through space, it moves as a wave, but also a particle. What is the name of that particle of light? That's called a photon. If you send a message back to Earth, it's still traveling 3 times 10 to the 8th meters per second, that's the speed of light, but due to its orbit, Mars is now further away, 4.01 times 10 to the 11th. We want to see how long it takes to send that message back. So we're going to use the same formula, plug in your velocity, plug in your distance. If the variable is down below, we can switch it out. So in my calculator, I type in 4.01 E11 divided by 3E8, 1,336 seconds. So when Mars and Earth are further apart, it takes more time to communicate. Projector in the communication center creates a small digital object, and a lens magnifies it to project on the opposite side of the lens. Is this a real or virtual object or image? This is a real image. This is because it's on the opposite side of the lens as the object that created it. Projector's lens is 0.1 meters from the 0.05 meter tall object. So this is the distance of the object and the height of the object, do and ho. It creates a 1.5 meter tall image. There's our height of our image, our high. What is the distance of the image created? We're solving for di. So look at our formula. We need di. There's a couple ways to find di, but only one that uses do, ho, and high, the information we already have. We plug in what we know to our given formula, simplify the top, simplify the bottom, and then we divide. 0.15 divided by 0.05 gives me 3 centimeters. That means the image created is 3 centimeters away. What is the focal length of the lens in this projector? Well, we're looking for focal length. There's only one formula for that. We need our do, the distance of our objects we were given, and our di, which we solved for. Now that we have our given formula, we plug in the information we know, simplify the top and bottom, divide, and there's our final answer. Our focal length is about 0.097 meters. This focal length is positive, so we know that it's a converging lens. It brings the light together. The distance between the common room's light and table is 1.3 meters. If you need to keep an illuminance of 50 lux on the desk, because this is a light level that people work best at, what is the required intensity of the light source? So now we're dealing with our brightness formulas. I'm given a distance away from the light. I'm given lux. If I look at my givens, lux is a measurement of illuminance. So we need to find a formula that has distance, illuminance, and can tell us intensity. So there's our formula right there. Notice the units, intensity, illuminance, and distance are all in there. We have intensity by itself. There's our formula. We plug and chug. 50 times 1.3 squared gives me 84.5 candelas. That's our intensity. That's how bright the light source has to be so that we can have 50 lux. So the brightness reflecting off the table. A dorm uses a light source with a luminous flux of 800 lumens. It's located 1.9 meters above your bed. What is the illuminance on your bed? So look at our formulas again. We're given luminous flux, we're given a distance, and we're solving for illuminance. So if I look, these formulas have luminous flux, illuminance, and distance all included, and this formula gives me illuminance by itself. The general original formula gives me illuminance. So I plug everything in, simplify the top and the bottom, makes it easier, and then divide to get a final answer. The luminous flux of a light source represents the amount of energy being released. What form of energy is released by light? If you think back to our forms of energy, we have radiant energy. Light radiates from its source. When a light source goes out, the other lights need to remain on. Which type of circuit allows the current to flow, even if part of the circuit is broken? We've explored that parallel circuits allow that to happen, and that's because they send multiple paths for the electrons, whereas a series circuit, if you break that one path, you've broken the whole circuit.